Welcome back to the show, everyone. Today, we're diving deep into the world of finance, specifically the challenge of hedging derivatives in a market that's far from ideal. Joining us is Shota Imaki, a lead researcher in deep learning and the mastermind behind a groundbreaking paper on deep hedging, and Dr. Emily Carter, a leading expert in derivatives and risk management.
Thanks for having me, Eleanor. I'm excited to talk about this research and its potential to transform the way we hedge derivatives.
It's a pleasure to be here, Eleanor. Shota's work is truly innovative and sheds light on the immense potential of AI in finance. So, Eleanor, let's set the stage for our listeners. What are derivatives and why are they so important in the financial world? And what makes hedging them so difficult? Great question, Dr. Carter. Derivatives are financial instruments that derive their value from an underlying asset, like a stock or a commodity. They can be used to manage risk, speculate on price movements, or even create synthetic assets. Think of them like a contract that promises a payoff based on the future price of something else. The tricky part is that real markets are far from perfect. Transaction costs are a reality, and prices don't always behave according to the neat mathematical models we'd like to believe in. These market frictions make hedging, which involves taking steps to mitigate risk, a complex and challenging task. Exactly, Eleanor. Traditional hedging methods, like the Black-Scholes model, rely on simplifying assumptions that don't always hold true in the real world. They often underestimate the impact of transaction costs and market volatility, leading to suboptimal hedging strategies. That's where deep hedging comes in, right, Shota?
Absolutely. Deep hedging leverages the power of deep neural networks to learn optimal hedging strategies, taking into account real-world complexities like transaction costs. The key idea is to train a neural network to make decisions about how much of the underlying asset to buy or sell at each point in time, based on the current market conditions and the desired risk profile. This approach has the potential to achieve far more accurate and efficient hedging than traditional methods.
That's fascinating, Shota. But deep learning models can be tricky to train, especially when dealing with complex financial data. Can you tell us more about the challenges you faced and how you tackled them in your research?
You're right, Eleanor. One of the biggest hurdles in deep hedging is what we call action dependence. The optimal hedging decision at each time step depends on the previous decision, creating a complex relationship that's difficult for a neural network to learn. It's like trying to solve a puzzle where each piece influences the placement of the next. To overcome this, we borrowed an idea from traditional finance called the no transaction band strategy. It's a strategy that says you should only trade when the current position deviates significantly from a predetermined range, called the no transaction band. This simplifies the decision-making process and reduces the amount of unnecessary trading.
That makes a lot of sense, Shota. By limiting the number of trades, you reduce the impact of transaction costs, which is a significant consideration in hedging. But how did you incorporate this strategy into your neural network?
We developed a new neural network architecture, which we call the no transaction band network. It takes as input the current market conditions and the desired risk profile and outputs a range, the no transaction band, where you wouldn't trade. The next hedging decision is then made by simply clamping the current position within this band. It's a simple yet elegant solution that effectively eliminates the problem of action dependence.
That's a clever approach, Shota. It's like adding a safety valve to the neural network, preventing it from making reckless trading decisions. Emily, what are your thoughts on this use of inductive biases in deep learning? I think it's a brilliant example of how incorporating domain-specific knowledge can significantly improve the performance of deep learning models. By introducing the no transaction band concept, Shota essentially guided the neural network towards learning a more sensible and efficient hedging strategy. It's a reminder that AI isn't a magic bullet. It's best when used in collaboration with human expertise and intuition. Absolutely, Dr. Carter, and those results are really impressive, Shota. Can you tell us about the experiments you conducted and the key findings?
Certainly, Eleanor. We ran extensive simulations on European and look-back options, which are two commonly traded derivatives, with a range of transaction costs. We compared our no transaction band network with a standard feed forward network and a benchmark based on asymptotic solutions for small transaction costs. The results were quite clear. The no transaction band network consistently outperformed the other methods in terms of expected utility, which represents the overall risk-adjusted return and price efficiency. The network also converged to a good solution much faster than the standard feed-forward network. This was particularly significant for the look-back option, which is a more complex derivative, showcasing the network's ability to handle path-dependent options.
So, not only does this approach deliver better hedging strategies, but it also does it in a much more efficient manner. That's a huge step forward for financial markets. Emily, what are the implications of these findings for the financial industry? Eleanor, these findings have the potential to revolutionize derivative pricing and hedging. With faster and more accurate hedging strategies, financial institutions can manage risk more effectively, potentially reducing costs and improving returns. It could also lead to more efficient and transparent pricing of derivatives, making the market more accessible to a wider range of investors. It's a significant development that could have a ripple effect across the financial landscape. That's a powerful statement, Dr. Carter, but there are always limitations to consider, aren't there, Shota? What are the areas where this approach could be improved or extended?
You're absolutely right, Eleanor. We made several simplifying assumptions in our research. For example, we focused on linear transaction costs and assumed a smooth payoff function for the derivatives. In reality, transaction costs can be more complex, and some derivatives have discontinuous payoffs. We're currently working on extending our approach to address these limitations. We're also exploring how to incorporate other market frictions, such as volatility smiles and term structures, into the neural network.
Those are important areas for future research, Shota. Emily, what other challenges do you foresee in applying deep hedging to real-world financial markets? Eleanor, the transition from theoretical models to real-world application always presents challenges. One major hurdle is the availability of high-quality financial data. Deep learning models require a massive amount of data to learn effectively, and the data needs to be accurate, reliable, and representative of the real market conditions. Another challenge is the need for explainability. While AI models can be very powerful, it's crucial to understand how they arrive at their decisions, especially in sensitive areas like finance. We need to develop methods to interpret the model's predictions and ensure that they are based on sound financial reasoning. Excellent points, Dr. Carter. These are areas where both researchers and industry practitioners need to collaborate to ensure that AI is applied responsibly and effectively in finance. Shota, what are your hopes for the future of deep hedging?
My hope is that deep hedging becomes a standard tool for financial institutions, enabling them to manage risk more efficiently, price derivatives more accurately, and ultimately make better investment decisions. I believe that AI has the potential to transform the financial industry, making it more transparent, efficient, and accessible for everyone.
That's a powerful vision, Shota. Emily, do you share that optimism? I do, Eleanor. The potential of AI in finance is immense, but we must remember that AI is a tool, not a replacement for human expertise. We need to carefully consider the ethical and practical implications of its use. By working together, researchers, practitioners, and regulators can ensure that AI is applied responsibly and for the benefit of all. Well said, Dr. Carter. It's a powerful reminder that technology is only as good as the humans who use it. Thank you both for this insightful conversation. Shota, your research is truly groundbreaking, and I have no doubt it will shape the future of finance. Emily, your insights into the practical implications are invaluable. I'm sure our listeners are eager to delve deeper into this fascinating world of deep hedging.